will be recorded. And Anna will present some numerical investigation of vortex formation in Bose-Einstein condensates. My pleasure.
I'm very happy to be back here in at the Hausdorff Institute, and really like home. So, yes, I'm going to talk about some numerical investigation that we did on this vortex formation in Bose-Einstein condensates. It's a joint work with my master student, who will start as a PhD now in the autumn, and Patrick Henry, he's here. So this is an outline of the talk. First, I want to introduce Bose-Einstein condensates and explain a little bit what this is. And then I will talk about the Gross-Kupelius equation that we use to model this. And we use it with rotation, because we're interested in rotating these. And I will speak about the finite element method. And as we will see later on, these are not always reliable. It has some multiscale nature. So my question is actually, when are these approximations reliable? Can we find a threshold for this? And we will see some numerical examples in the end. So bosons, they are a class of quantum particles. So this one is like a little scheme of the different quantum particles. So these are the bosons, you have the hadrons, and the fermions. So you probably recognize like the photon and the Higgs particle, they are bosons. But they are also composite particles that are bosons, like the helium-4 isotope, for instance. It all has to do with the speed. But I will not dig too deep into the quantum physics. I want to focus on math. So the Bose-Einstein condensate, it appears when you cool a gas with bosons to ultra low temperature, so near 0 Kelvin. And at that state, all the particles will occupy the same quantum state. And it will no longer be possible to distinguish them from each other. You can think of them as they form a kind of a super particle. So this is sort of a picture that I would like to just describe how they are formed. So this is in the beginning when you have quite a high temperature, and this is you have the bosons move freely. They all have different energy levels. You decrease the temperature, and they start to move less. And you see, because of their quantum nature, they have this wave behavior. So they will move less freely, and they start to decrease in energy. And as the temperature gets very close to the 0 Kelvin, they will all fall to the lowest energy state and form this giant wave. And this is what we want to model, the behavior of this. And it forms a new state of matter. It's called Bose-Einstein condensates. It's an exotic matter. So usually we have this like the solids and the fluids and the gases, but this is an exotic type of matter. And it's quite interesting because now we're able to observe quantum phenomena on a macroscopic scale. So one example that we also want to study in this work is superfluidity. So this is a fluid with 0 viscosity. It's able to move without friction. So this is what it can look like. So this is a superfluid. It's formed by, like, for instance, cooling like this helium-4 isotope. And this is actually pictures from an actual experiment. So when you rotate a superfluid, so I think it might be helpful to think about, you have your cup of coffee and you stir it, and you get one vortex if you are lucky and you spin enough, right? But when you spin a superfluid, you get a pattern of vortices. And if you spin it really fast, you get lots of vortices. And of course, you don't use a spoon to stir. Usually it's some kind of magnetic trap, or you use a laser beam to stir it. I think this next actually, here you have the formation of the vortices, and then you disturb it a little bit by shooting it with some laser, I think. And then it finds back to its sort of ordered vortices. But we're interested in this part, how to model this, these vortices, the patterns. Yes, okay, so this is not my work. I don't work with these experiments. This figure is from, I have a reference here, some English colleague from Hamilton Chartpad and from.
So sorry, does it mean that the vortices can all spin in the same direction? If there's no viscosity?
Yes. So they have the vortices in, they are like the quantized vortices. So depending on how fast you rotate it, you will get different patterns. You'll see some examples later on. Okay, so we use this Gauss-Pythagorean equation, which we want to model the stationary states. So it's the ground state of the Bose-Einstein condensate, and we include this rotational term because we're interested in rotating. What happens when we rotate the condensate? So it looks like this. You have your Laplacian. This is a trapping potential. You have a nonlinear term. This is a rotation. So it's a nonlinear eigenvalue problem because of this term. So B is just your domain, where you want to compute your Bose-Einstein condensate. And B here is the trapping potential, as I mentioned, and we assume it's in an infinity. So it's quite nice. It's in an infinity at least. So this data here will, it's a positive number. It will depend sort of the number of particles you have and what type. And this LC operator here is the rotational term, so it's rotation in sort of the Z axis. It rotates by using this term. And this omega will be the rotational speed. Okay, so to ensure existence of a solution, so we will need the following assumption. So this actually connects your trapping potential and the rotational speed. So if you spin it too much and your trapping potential is too weak, it will break due to centrifugal forces. It will just disappear. So you have this assumption to ensure that you have a solution. So you have a trapping potential, you have 1 plus epsilon, divided by 4, and then omega squared, x squared plus y squared. So so this connects the trapping speed, the rotational speed and the trapping potential. So instead of solving the nonlinear eigenvalue directly, we usually go through the energy functional. So we define the corresponding energy functional to this problem. It looks like this. You have the flare coming from the Laplacian, you have trapping potential, this comes from the nonlinear terms, and this comes from the rotational term. And then you can achieve the ground state by solving the minimization problem. So you want to find a state that gives the minimal energy. So you have your H10 space, and you also constrain it because you need to conserve the mass. And once you have your ground state, you can retrieve the corresponding eigenvalue by using this relation. Okay, so this is what it can look like when we run some experiments. So this is for this trapping potential. It's a smooth harmonic trapping potential. So when you spin it, the omega, I should say also, but in this setting, omega is bounded from above by 2, so it cannot go above 2. So you have 1, which is a pretty low speed, you have 1 vortex, and then you speed up to 1.4, you get more, 1.6 even more, 1.75 even more. Okay, so now let's discuss the finite element method, or how do we actually compute these minimizers. So instead of having this infinite dimensional space, I will replace it by the H here, which is the classical P1 finite element space of piecewise and continuous elements. And yeah, you just replace it over your minimization problem, and the corresponding minimizer is UH. The H here is connected to some mesh. And yes, you can retrieve the same eigenvalue by using your approximation UH. And now it's possible to prove an H1 bound for this. And it's sort of what you would expect. It's A, you have the finger, and it depends on the H2 norm of U. Okay, but when I compute for different mesh steps, this is what my error graph looks like. So for what we look at here is the error, the H1 error for different step sizes, and a fixed rotational speed. So we start here, and nothing really happens, and then at some point, the convergence starts, right? So we get this sort of pre-asymptotic behavior due to multiscale nature. And the question is, can we sort of predict where this is? It's a non-trivial question, right? Because you cannot really determine a fine scale by simply looking at V or omega. Let's go back to the equation. So it's not your classical multiscale problem where you have diffusion coefficients, which is rough or highly varying. I mean, the vortices appear from a combination of the trapping population and the trapping speed, rotational speed. So it's an interplay between these, right? And V here can be smooth, as we have seen. This can be smooth, and this is just a constant. So it's not. So I mean, in your typical classical multiscale problem, you have an epsilon that you sort of know that if you go below this epsilon with the mesh size, it's fine. I know that I can at least trust the finite element approximation. But in this, I would like to compute, or sort of say where is this? Okay, so let us compute a little bit. So recall this error, the H1 error. We have this bound. And this is the Gauss-Betesky equation. But now I move everything except for the Laplacian to the left, to the right hand. So the reason that I did this is because I want to use elliptic regularity theory. So I want to prove something for the H2 norm of U. And using elliptic regularity, okay, this is V here is in L infinity, so this term is okay. This one is okay. This is a first order differential operator, also. And this is also a nice term. The one that sort of determines this bound is the nonlinear term. So it's you get this U squared times U, and this is the reason you get the power 3 here. So we can bound the H2 norm by the H1 norm to the power 3. So we would like to bound the H1 norm, because then we know the bound for H2 norm. And using this, I want to introduce a new norm, which is, I call it R norm here. The way to do this is to introduce a new covariant gradient. So this is a sum of two parts. It's the normal gradient plus your rotational term times this r, which is, it comes from the rotation, it's x2 minus x1. And then you modify your potential a little bit. I call it VR. So you have your true potential, V, minus this omega squared divided by 4 times this, the absolute value of x. And this is now greater than 0. This we know due to this assumption we had with the epsilon. And using these two, we can define a new inner product and the corresponding norm. So this is my R inner product is the gradient using these R gradients and the product between these two, and using my new trapping potential VR, we get this new inner product. And with this one, we can prove equivalence of norms. So the R norm is equivalent to the H1 norm. So we can now bound this minimizer U from the ground state in H1 norm by using this equivalence of norms. And so you get the R norm is now, the reason we did all this work with the R norm is that it's now easy to bound using this energy. So this is directly gives us that it's bounded by the energy. And since U is the minimizer, we can replace U with any function. So you can choose some bubble function of some sort, and you can bound it by a constant. So it seems that this constant that comes from the equivalence of the norms can give us some information about what happens with the H1 norm of U. So we'll try to compute it. So one might ask, why don't we just do it by hand? This we have tried in terms of the epsilon, in the assumption that we had, but it's turns out to not be sharp. So what we want to do instead is to solve, to get this CR by solving the eigenvalue problem. So this is the eigenvalue problem that I want to solve. I use the R inner product and the H1 inner product, and I compute the eigenvalue, and I choose the minimum one. This is also the minimizer of this Rayleigh quotient. It's you need to prove. I will not do the details here, but you can prove it. That this minimizes, it's the minimizer for the Rayleigh quotient. So if this is true, you just okay, then you can plug in your ground state. I also call it the minimizer. It's the minimizer of the energy function, not the Rayleigh quotient. So this is my ground state. I plug it in, and I know that okay, it's greater than or equal to this minimal lambda, minimal eigenvalue at least. And this gives me the following relation. So my CR that comes from this equivalence of the norms is the square root of this minimal eigenvalue. I use a hat on it to, this is not the same eigenvalue as in the Bose-Einstein equation. So if my H1 norm is bounded by this, I can plug it in for, oh sorry, this is a typo. It should be H1 here. So the error in the H1 norm is bounded by this 1 to the power 3. This we saw before, that the H2 norm of u was bounded by H1 norm of u to the power 3. So it seems that this could be my thing. So it looks like we should need that h is less than this minimal eigenvalue to the power 3/2. And what is sort of good to note here is that this minimal eigenvalue depends on your trapping potential and your rotational speed. Of course, it connects them through this R norm. And it's not easily computed, and you don't have to have knowledge of U, of course. You can solve this with easy eigenvalue problem before solving the Gauss-Bethe equation, of course. So this is, otherwise this would not be a good result. So you compute it first, and you get a rough estimate what should my mesh size be to get a reliable solution from the finite elements. So you need, of course, to use some eigenvalue solver for this. That it's considerably faster and easier than solving the true Gauss-Bethe equation, which is usually an iterative process where you need to find the minimizer of U. The minimizer of the energy function. So let us look at some numerical examples. So I have lots of them. I start with the case 1. This is where we saw in the beginning, where you have the trapping potential, which is isotropic. So it's the x squared plus y squared. You have a rather high, but this is considered a high value. And I approximate my minimal eigenvalue, that will give me the bound of h, on the same domain. Yeah, so this is what we saw earlier for different rotational speeds. This is what I call case 1. And this is the H1 norm. So what we look at here is the H1 norm of U, and I would expect it to behave as minus the eigenvalue, minimal eigenvalue to the power of minus 1/2. And this is also what it seems to be doing. These marks here are the rotational speed, and this is lambda min to the power of minus 1/2. So it seems to follow that pretty well. Yes, okay. So now I would like, of course, to compute the error bound, to see if this threshold really holds. But unfortunately, for this round, this isotropic case, it's quite hard to, it's very sensitive to, so what you should know is that the minimizer is not unique. You can always rotate it a little bit and you get a different one. So when you try to compare two, which one is computed on a coarser mesh with something that is computed on a finer mesh, even if you have two good solutions, they can appear as the error is large because it's slightly shifted. So this is, in this case, unfortunately, I cannot compute it, not yet. It's a very tricky numerical problem. What one can do is to look at a slightly, or an anisotropic case, which is not completely round. Then it's a little bit easier because it forces the vortices to be more in the same place for different meshes. So what I do now is to choose this trapping potential, which is has 1.1 squared in front of y. So it's slightly anisotropic. Also, I reduced my beta a little bit because it gets less messy, so we have less vortices. So we compute a reference solution on some fine mesh, and I compute finite element approximations on coarser meshes. And as before, my indicator here, the lambda minimum, is approximated on the same domain. So it's also approximated on this square. So this is what the anisotropic case looks like for different rotational speeds. So this is for 1.6, 1.7, and 1.8, the rotational speed. So you can see that it's sort of pushed a little bit in the y direction. So this is easier to compare solutions in. At first, you can look at H1 more, similar experiment as before. It should be like the minimal eigenvalue to power minus 1/2. And this is roughly what we see. Maybe it flattens a little bit in the end. Could be because we sort of approach the maximum allowed value for omega. It's supposed to be 2, the upper bound, so 1.9 is quite close. But now we can compare the errors. So this is my H1 error. This is the blue line, and this is H, the dotted line here. And this is my computed minimal value of lambda to about 3/2. And as you see, for omega 1.6, exactly is what you can find. So before this line, we have no convergence, we have this pre-asymptotic behavior, but after this, we get better speed. For 1.7, it also looks good. This was the one we looked at before in the first slides, but I had question marks here that I wanted to find. So this is the lambda to the power 3/2, giving us the result here for omega 1.7. And this is for 1.8. It's predicted to be here, the H1 error. It's not as good in the other two plots as in the other two plots. One should also keep in mind that, of course, this lambda is approximated by also using a mesh. So it's not exact, it seems to be in the right regime. But actually we tried to increase the domain a little bit. So usually what you do, you choose your domain, it's usually a square, where your condensate lives, and it lives inside that. But so visually it seems like this domain is okay, but increasing it a little bit actually seems to give better results. So both the eigenvalue, this lambda minimum here, and the solutions are now computed on the bigger domain. And here it seems to get a better prediction. So my third case is a more anisotropic potential. So this is more pushed in the y-axis. And here all the vortices will lie in one line. We'll see it on the next slide. So beta is still 200. A pretty low value, I think. And as before, I compute the reference solution on some finite mesh, and the finite element approximations on Persson meshes. And this I compute on the same domain as usual. So this is what it looks. Oh, did I not include? I'm sorry, I think I forgot the pictures. So what they look like is, I had the graph, but now I will draw. So it's now more, I added this last minute yesterday, so I will blame that I was tired maybe. So it's usually, so the other ones had like vortices all around, but this one it looks like a flat thing like this, and the vortices appears like this. And the more you increase the speed, the more the rotational speed, the more vortices you get, but they're still on one line.
So what happens in this pre-asymptotic regime? You do not see the vertices, or they are in the wrong
They are usually not enough. They're too few.
Ah, okay.
And not in the right place. So you have the wrong pattern and the wrong number. So that is why you get this is such high. So when you approach this value, you start to get the correct number of vortices, and you start to get convergence. Okay, so for 1.8, this prediction is here, which is not good. And for 1.9, it overestimates a little bit, but still a pretty nice estimate, I think.
Maybe I ask my question now because other people are already asking.
Yes.
So I mean, for me, I wouldn't worry too much about whether it's not exactly on the right point because, I mean, at one point you made the link between h times c times lambda mean to the -3/2 and said h should be less than lambda -3/2. There's the c as well. And
Yes,
the c depends on omega and on v, and so...
Yes, so it's not exactly, it's not expected to be.
So what do you observe C to be? Because I think one of your plots, you had these two lines that came down. It looked like for that example, it was about 2 or 3, or 1 point, or a half or 1/3. I don't know in which order the C appears. At the very beginning, you had the curves going down with the line. Yeah, exactly. And there you've got this factor 3 in some sense. There's 3 in some sense. So I think that's something to do with the constant, no?
Yes, it could very much be.
Okay.
So two things. There is an additional constant, and there is an approximation on the finite element grid. So it's still so it seems to work out pretty well, I would say. So I would also like to mention some future work. So now, when we have this bound when we know when the mesh sizes are reliable, or when the computations are reliable for finite element method, it's now interesting to actually have a multiscale approach and get efficient computations in this pre-asymptotic regime. So here I would like to have another method which doesn't push me to be here. I would like to be here. So since I'm from the LOD community, we would like to apply LOD to this one. And it's actually a nice kind of, it's not trivial, because now I would like to, I see I have some time, so I can discuss this. Let me just find this one will do the equation here. So if you, when you use the LOD method, you have your bilinear form A, which comes from usually your diffusion coefficient, which these spaces are. You have this multiscale space, and you have your fine scale space, and they are orthogonal in some bilinear form, which usually comes from your constant, your bilinear form A, which includes, this one I should point out, your Laplacian, because you have a coefficient in here which is tricky. And so the question is, what is a proper choice in this case, which is not a classical multiscale problem? So of course you should have this one, but this one is probably not enough. You can include the potential. This is what they did without the rotation. We included this too. This we already have results on, and this works well. But the question is, should you also add this one, the rotation? It feels natural to include it because the omega decides how many vortices we have together with the trapping potential. Right. So somehow giving the multiscale space knowledge about this rotational speed seems like a good thing to do, right? But some preliminary results seems that this is not needed. We only need these two. I don't know why really, but it's so this needs further investigation. We are working on this. Yeah, so this was the question, how to define an appropriate multiscale space, or maybe we should do something completely different. Maybe this is still open. I think it's interesting. So, yes, so with that, I would like to thank you for your attention.